All right, chapter 6 is on the normal distribution. Many populations have a distribution that is normal or approximately normal. It's probably the most well known in statistics and out of statistics as well. Things that have a normal distribution, errors in measurements is one thing. Yearly rainfall, lifespans of consumer goods, human heights, and maybe of particular interest for us are sample means or X bar. Normal distribution, if we have a graphical representation of the PDF, it is symmetric and it has that bell shape. And even though this graph doesn't have it, we can still assume along the bottom are the values of x, the values that the random variable takes on, and the vertical is the function, which I showed that briefly, I think, in one of the last videos, and it's one that we're not actually going to use, but we can, still think of that curve is arriving from plugging in values of x and getting a function value. Okay, so this first example is lifespans of light bulbs. So you can see that it ranges from, somewhere less than 1,800 hours to something more than 240 hours. And right there in the middle is the mean. Okay, and we're going to learn more about characteristics of the normal density curve, but we can just kind of focus on that for now. Another example, we've got men's and women's heights both follow a normal curve, have that symmetric look and that bell shape. Okay, we're going to fill in those blanks underneath. Let's look at the characteristics of a normal random variable. A normal random variable is uniquely defined by the mean and standard deviation. So again, like uniform is defined by the minimum and maximum value, and binomial defined by n and p, the normal distribution has the two parameters that it's defined by. So if x is a normal random variable, so we identify that with an n, what we need to know is the mean, mu, and the standard deviation, sigma. The density curve is perfectly symmetric, and it's symmetric around that mean value. And the standard deviation, sigma, is what's going to change the shape and the spread of the curve. The total area under a density curve, like all density curves, is 1. And we're going to find probabilities just like we did for other continuous random variables. If we want the probability that x is between two values such as c and d, it is going to be the area under the curve between those two values. So we can represent it like that. We're going to be finding probabilities, those areas, from using a tool, an online tool, or other means of technology. Okay, so let's take those characteristics and go back to our examples we have up here. Lifespan of light bulbs. We can uniquely define this random variable by putting in the mean and our estimate of the standard deviation. So it's easy to pick out the mean value. It's that middle value, so that we can see that the mean value is 2100. All right, standard deviation isn't readily available from just looking at the density curve, but one standard deviation on either side is where the graph changes from being concave down to concave up. So it's approximately at 2200, which is 100 over that mean of 2100. So we can estimate that the standard deviation is 100. Okay. We look at women's heights and men's heights. Women's heights, the mean there is 65, it looks like. For men's height, it looks like the mean height is 70. All right, so again, if we try to sort of kind of eyeball the standard deviation, we kind of want to look at where the graph is kind of changing from curving down to curving up. And it's really difficult to see, but I'm going to say it's about at 68, which would make the standard deviation for women 3, And for men, I'm going to say that it looks like it's at about 75 that change happens. And so we'll say the standard deviation is 5. But a couple things to notice here is that with the different means, we can see that the placement of the density curve along that x-axis changes, right? Going from the mean of 65 to 70, it shifts the graph to the right. So it's changing the location of the graph along the x-axis. So mean changes location of the density curve. And then if we compare those standard deviations, the women distribution is standard deviation of about 3, and we can see it's less spread out than the men's, which has a larger standard deviation. Okay, so that would be a way that we can kind of think about what's happening with the standard deviation. Smaller it is, the less spread out it is. All right, but the smaller the standard deviation and the less spread out it is, the peakier or the higher the density curve. Okay, because it has to have that same area of 1 underneath, so to accommodate all that, it has to be higher to include it. Okay, this first section in chapter 6, we're going to look at a particular normal distribution called the standard normal distribution, and then also something called the empirical rule. Okay, let's look at this normal random variable, standard normal. It has mean of 0, standard deviation of 1, and we use a z to represent the standard normal. So if you see z, we can immediately know that it's a normal and it's got mean of 0, standard deviation of 1. So normal, 0, and 1. All right, it also is symmetric around its mean, which is 0. The total area under the curve is 1. So if we take the curve and we look at area to the left of 0, that area is going to be half of the total area of 1, and the area to the right is also 0.5. All right, that's going to be the case for any normal distribution. The area to the left of the mean is 0.5, area to the right of the mean is 0.5. All right, if we calculate the z-score, all right, going back a chapter or two, of a value from a normal random variable, it converts it to a standard normal random variable. So just as a reminder, to calculate a z-score, we take whatever value we have, we subtract the mean. Okay, if we're subtracting the mean, we're kind of like taking it down to 0, like the mean of the standard normal. And then we divide out by the standard deviations, and that gives us the z-score. And also a little bit of review, remembering that z is equal to the number of standard deviations away the random variable value is away from its mean. Okay. All right, let's look at an example. So we starting off with a normal random variable that has mean of 10 and standard deviation of 2.5. So if we take this density curve here and label it for this random variable x, okay, we can label the mean as 10, and then we can calculate the z-score for that particular value and convert it to a z-score. So 10 minus, actually let's back up, we want 15, we want the x value, minus the mean of 10, divide by standard deviation of 2.5. So we get 5 over 2.5, we get a z-score of 2. Okay, so now remembering that the z-score is the number of standard deviations away from the mean, now let's take another look at that density curve, and let's think about what it means to have standardized this value. Let's look at another horizontal axis with that same density curve above it. Now if that's the z axis, all right, we can take that middle value, and that is now 0, the mean of the standard normal. Now we just determined that 15 has a z-score of 2. So just kind of going 2 out, we determined that 15 is 2 standard deviations away from the mean. So, okay, the relationship between 0 and 2 is the same as the relationship between 10 and 15 in our normal random variable with mean of 10 and 2.5. Okay, so by standardizing it, we can kind of get an idea of how many standard deviations away a particular value is from its mean. And in this case, we know that 15 is 2 standard deviations away, or we can even be more specific by saying above the mean. It's in the positive direction. Okay, sometimes we're even asked the question about how many standard deviations away a value is from the mean. So here we've got value 6, and we can just kind of label our density curve again, and we're going to want the z as well. Okay, so first thing, we calculate that z-score, that z-value. Take 6 minus 10 divided by 2.5. Okay, 4 divided by 2.5. That gives us a z-value of negative, actually this should be a negative 4, so negative 1.60. Okay, so I guess one thing I should say is these little marks that we have on the axis, the horizontal axis, at least for a z, those represent standard deviations. So if we want to put that negative 1.6 on there, all right, we got it right about, a little bit, right about there. So that would be the negative 1.6. All right, so that gives us the relative distance away 6 is from 10. Okay, so we could put the 6 right there. And so we could say that 6 is 1.6 standard deviations. And because it's negative, that means it's less than or below the mean. Okay, now let's go the other direction. What value of x is 2.5 standard deviations above the mean? Okay, taking our density curve, here's our z, and there is 0. Okay, so we have 1 standard deviation, 2 standard deviations, 3 standard deviations. All right, right there we have got the z value of 2.5. All right, that gives us where we have 2.5 standard deviations above the mean. So we're looking for the value of x, the comparable value of x from this distribution that has the mean of 10. Okay, so we know the z-value. So 2.5 equals, and what we're looking for is x. We don't know x. We can subtract the mean from that value, divide by the standard deviation, 2.5, and now solve for x. So 2.5 times 2.5 is 6.25, and then we add 10. That's going to give us x. So x is equal to 16.25. So 16.25 is 2.5 standard deviations above the mean. Okay. Another thing that z-scores allow us to do is not just z-score. So z-scores can allow us to standardize any normal random variable, and we're going to see later why that's important. We also can compare data values that are scaled differently. And we looked at this a little bit when we looked at z-scores before. So we have this example from basketball. Emily averages 18 points a game with standard deviation of 4 points. Brenda averages 16 points a game with a standard deviation of 2. And we're going to assume that the points scored in a game is normal. So if we look at the distribution for Emily's points, we have that it's normal, and we have a mean of 18 and standard deviation of 4. And Brenda, standard normal distribution, mean of 16, standard deviation of 2. Suppose in a game Emily scores 20 points and Brenda scores 17. Who scored more points? All right, so here's where we want to compare Emily to her own record and compare Brenda to her own record and compare that way. Okay, so this is asking us to find the z-score. So let's start with Emily in blue here. So she scored 20 points. So plugging that in, subtract 18, divide by 4, we get z-score of 0.5. And now let's look at Brenda. All right, she scored 17. Subtract her mean of 16, divide by 2, and we get 1/2 or 0.5. All right, so it turns out that they scored the same compared to their own average. Okay, now let's talk about this empirical rule. If we have a z-score and we know this empirical rule, we're going to be able to estimate probabilities for a normal random variable. All right, so the empirical rule actually applies to any distribution that's symmetric, not just normal. And what it says is that approximately 68% of the values will fall within one standard deviation of the mean. So when we say within one standard deviation of the mean, we're talking about from one standard deviation to the left to one standard deviation to the right. Okay, so this area in here contains 68% of the value, or we could think it contains just 60% of the area. So 68%, one standard deviation, within one standard deviation of the mean. All right, then it says 95% of the values will fall within 2 standard deviations of the mean. All right, so that's from -2 to +2 standard deviations. So that area we can think of as being 95%. So within 2 standard deviations for a normal or any other symmetric distribution, 95% or almost all of the values are in that area. And then finally, if we go to 3 standard deviations, within 3 standard deviations of the mean, we get pretty much all of the data values, 99.7. Okay, so that's just essentially 1. It's essentially 100%. Okay, now I just want to tie this back to when we talked about z-scores before and when we talked about outliers, and we said that if a value has a z-score that's above 2 standard deviations or below 2 standard deviations, okay, so above 2 or less than -2, then we want to consider it an outlier. Okay, well, this is why right here. So you can see if it is right in here or in here, all right, that's a really rare occurrence, okay? 2.5% chance that that's going to happen. That's why we kind of use that cutoff of 2. Okay, so now let's use that empirical distribution to estimate some probabilities. So what is the approximate probability that Emily scores between 14 and 22 points in a game? Okay, so we can start with our density curve here. And again, we're going to kind of look at these two scales, the X and the Z. And for the X, for Emily, right, we've got mean of 18. Okay, and what we're looking for is the approximate probability that she scores between 14 and 22. So first thing to do is to find the z-scores for those two values. So take 14 minus 18 over 4. Okay, and that gives us negative 4 over 4, so we get a negative 1. Okay, so if we want to relate that to the z here, you got negative 1, so 17 or 14 is right here. And do the same thing for 22. All right, so here we have a positive 4 over 4, so we get a positive 1. So z-score of 1 is going to relate to x value of 22. Okay, so we are looking for this shaded area right here. And because the 14 is 1 standard deviation to the left and the 22 is 1 standard deviation to the right, what we have is within 1 standard deviation of the mean. Okay, so that probability that x is between 14 and 22, all right, that's equal to the probability that z is between negative 1 and positive 1. And by the empirical rule, we know that that probability is approximately 68%. Okay, we're going to get to the place where we find exact probabilities, but we can just, based on this rule, say that it's approximately 68%. Okay, here's another probability to approximate. We want the probability that Brenda scores more than 18 points in a game. So the probability that x is greater than 18. We want to convert this to a probability about z. So we want to fill in z is greater than what value. So looking at the density curve for x, we have it centered at 16, and for z we have centered at 0, and let's calculate the z-score for 18. 18 minus 16 over 2, that's going to give us a z-score of 1. Okay, so 18 z-score of 1, so we can put that on the density curve. The area, the probability that we're looking for, the area is everything to the right of 18, or what we call the tail of the distribution. Okay, now we can fill out our probability. We want the probability that z is greater than 1. Now this isn't one that we can find directly from the empirical rule, but if we think about what we have here, we know that everything to the right of 0 is 0.5. Okay, and then we know that everything between 1 standard deviation to the left and to the right is 0.68. And because of the symmetry, that means between 16 and 18, all right, that's going to be half of 0.68, so that's going to be 0.34. Okay, so if we take the whole area to the right, which is 0.5, and we subtract off the piece that is not included in the probability that we're looking for, the 0.34, All right, that's going to give us 0.16, and it's going to give us that area that is in the tail that is shaded. That is greater than, where x is greater than 18, where z is greater than 1. All right, look at another one. What is the approximate probability that Brenda scores between 14 and 20 points in a game? So we want the probability 14 less than x less than 20. So we're going to want to convert that to a probability with z. Okay, if we can look at our density curves, and let's convert to z-scores. So we have z equals 14 minus 16 over 2. So that's going to be a -1, and 20 minus 16 over 2, that's a +2. Okay, so we're going from a -1 to a +2. So labeling the x-axis, we'll put the 20 with the 2 and the 14 with the -1. So we are looking for this area between 14 and 20. Okay, which is also the area related to z between -1 and a +2. Okay, so again, this doesn't come directly from the empirical rule. If we split the area to the left of the mean and the right of the mean, to the left of the mean, we've got 1 standard deviation. So that's going to be half of 0.68, so 0.34. And then between 16 and 20, we have 2 standard deviations. So, you know, within 2 standard deviations, it's 0.95. So if we just look at half of that area, and cut that in half, that's going to give us 0.475. So we add those two pieces together, 0.34 plus 0.475. Okay, that gives us approximate area of 0.815, or approximately 81.5% of the scoring that Brenda does is between 14 and 20 points. And I should also make this approximate too, if I'm going to be consistent here. Okay, that's it for 6.1.